Leaking rivers in Brazil, USA's oldest rock, volcanologists improving urban climate resilience, and lithium mining in Oregon. Welcome to the Geology Hour, our monthly gathering of geology enthusiasts, brought to you by the Geological Society of the Oregon Country, with support from the Beverly Vogt Scholarship Fund and the Portland State Department of Geology. Hello, I'm Paul Edison-Lam.
I'm Carrie Gordon.
I'm Emily Cahoon.
And I'm Melissa Smith.
It's our 5th anniversary today. We started this, like so many things, in 2020. And I have a lot of people to thank. Among them, the folks in the room who make this possible. Gary Joquin, who joined us when I started to realize that I couldn't handle all the background technical stuff, and so he's our technical director. And Carrie Gordon, who, when we realized we need a professional geologist to be asking the questions and hosting, has been with us for several years now, and especially Alyssa Smith, who is our graduate student from Portland State, who has taken the geology news segment, which formerly Andrew Dunning had worked on, another graduate student. She's taken it to new stratospheric heights, or I don't know, whatever the sphere you'd want to use to describe it geologically, I'm not sure, but and really made it a professional segment of good reporting. So all of those, and also Carol Miles, who's not here, who heads the Beverly Vogt Committee, because we couldn't do this without the support of our members and donors who contribute so that we can pay our grad students, whose time is valuable. We are so grateful to have folks here at the vanguard of the profession. We're really lucky to have their contributions. And then finally, all of you, some of you who've been with us for the whole 5 years, we really appreciate your contribution as members of the audience. And sometimes some of you, as you know, have been pulled in from the audience to give presentations. So we look forward to that in the coming months. And here's Alyssa Smith.
So this is my segment I've been calling Geology in a Nutshell, where I'm going to go over just some kind of recent geology news. So the topics today are going to be leaking rivers in Brazil, a quest to find the USA's oldest rock, and volcanologists' connection to climate resilience. So starting off with this article about leaking rivers in Brazil, I'm going to talk a little bit more about what that means. So there's an Eos Summary article and then a full article that you all will be able to reference. So we're starting off in Brazil, so northeastern Brazil, especially the São Francisco River, and that is in this kind of area here. And back in about 2017, there were a bunch of reports from the area where people were reporting spikes in like high blood pressure in this region. And what it was determined to be is there was some sort of correlation between the dry climate at the time and low river flow. So what this study did is it linked health issues with the dropping water table in this region that was then being infilled with salt water from nearby bodies of water. And so one of the things that was causing it is going to be kind of the slowing of stream flow that was ultimately caused by the overpumping of wells in this area. So this study particularly mapped rivers and looking at areas of at risk or that were currently undergoing water loss. And they looked at data from over 18,000 wells. And what they determined is up to 60% of the rivers in this area were considered critical regions for losing water. So what does that mean? So what this graphic shows is the well water level and groundwater level here. And in this situation where the well water level is above stream level, and you've got groundwater that's flowing into the stream, which is normal. But if the well water level drops below that stream level, then you have stream water that seeps into the aquifer. And so whatever's in that stream is then going to be percolating into water reserves. So this is a map from the study, and the blue there is going to show areas where the groundwater is or essentially the well water is above the groundwater level. And then the red is where you've got the reverse. So not a great situation for a significant number of wells in this area. So essentially this uncontrolled expansion in this area of people, adding additional wells, a lot of excessive pumping is going to be affecting health and water supplies, agriculture, and potentially causing land subsidence in the future. And so this exploitation of resources has been basically due to a lack of funding in the area and a lack of surveillance. A lot of people drilling their own wells without authorization. And then there's also a regional kind of misunderstanding about where water is sourced. People think that most of it comes from the rain getting into the rivers, but they don't understand the connection to aquifers underground. And so this study therefore highlights the need for people to do more research and to have more monitoring of wells to determine kind of the long-term impacts. And now we're going to transition back to rocks. So this is an article that was from GSA Today, a news source for me today, for trying to find the oldest rock in the United States. So we're going to start out with a map here of basement geology. One of the things that is known, if we were talking about the oldest rocks in North America, is the Acosta gneiss up in Canada is the oldest known rock in the world. But that's across the border. So if we're trying to think what's going to be the oldest thing next to us, we can look at the basement. So this is showing just generally how old the crust is in different parts of the United States. So there's some locations on there. We're going to get to those in just a minute. If you're not familiar with the geologic timescale, it's totally fine. So this is the division of geologic time, and we're going to ignore 75% of this chart, which is not 75% of all time. We're going to go over here to the Precambrian and narrow in on the Archean. So the Earth during the Archean eon was significantly different than it is today. The Archean took place from about 4.5 to 2.0 giga-annum, so billion years ago. And this was a time of rampant volcanism and a very simplistic life, some of the earliest forms of life on the planet. So those little blob things in the water there are stromatolites, which are one of the earliest records we have of life on Earth. And just, yeah, the sort of processes that went on at this time are largely inferred because very few rocks from this time exist. So if we're looking just at the red area here, which I crudely cut out on this map, these are showing the locations of Archean crust on the United States, like country, so not continent. The Watersmeet gneiss should also be in red there too. Technology is difficult, but yeah, this is showing the Sakawi gneiss, the Morton gneiss, and the Watersmeet gneiss. So those are the three candidates that this study had for the oldest rocks in the United States. So let's take a look. So here's the Sakawi gneiss, and this one is a trongiamite with biotite gneiss. So it was a trongiamite, now it's a gneiss. That is just an extremely foliated rock. The scale there is 15 centimeters. Then the Morton gneiss is the one that kind of the article starts talking about. It's just described as a gneiss, but there's a pencil there for scale. And then the Watersmeet gneiss is a biotite tonalite gneiss. And there's a pencil for scale there too. So wouldn't necessarily know these rocks are as old as they are, but now you do. So the method that is used for dating these rocks is uranium lead dating. And this is optimal for igneous rocks, old igneous rocks. They have to be rocks that have a lot of silica in them, a lot of zirconium, because what they date in it is zircon. So the process itself, the quantum process, is radioactive decay. And so there are two uranium isotopes that we'll use for this form of dating that will decay to lead. And we use the two different forms because they act as independent clocks from each other. So what we can imagine is we have a rock here that originally has just a bunch of uranium. And then over time, that uranium, the parent atom, will decay to the daughter, which is lead in this case. And so as time passes, more and more of that uranium will decay to lead. And it's actually a much more complicated process than that. But this works. So the more lead you've got in the rock, the older the rock is. Now, so if we're looking at a rock, we're not actually just dating the entire rock in this case. We are looking at zircon crystals. And so zircon is an element or an okay, let me try that again. Zircon is a mineral that is common in these kinds of rocks. It's an extremely resilient mineral that will kind of keep itself mostly intact over literally billions of years. And so the formula is you've got zirconium and silica, and then what can happen is that uranium fits really nicely into the spot that zirconium would be in. And so uranium can sub in for zirconium as the mineral is crystallizing, and everyone's happy. But the problem is it doesn't stay that way. So if the uranium decays to lead, lead is a different size. It's still a rather large atom, but it oftentimes will have a different charge. And neither of those things fit really well with minerals. And so if the rock is heated up, then the lead can actually leave the crystal, and that's called lead loss. Surprise, surprise. So what can we do about that? We can't just throw our hands up and be like, okay, can't date the rock now. No, we can use our two different isotopes of lead, two different isotopes of uranium, and form a diagram. So this red line, or this pink line, is the Concordia line, and that is that's a line that's like a global line for these four isotopes and where the ages agree. So each of the dots on here represents a different time period, and so excellent. Now, if we are to add on dates for rocks or minerals, and they land on the line, those are called concordant, and they're just things that land on the line, and essentially the age that point is the age of the rock. Excellent. But I'm guessing you might be thinking, well, what if it doesn't? Those are discordant ages. So typically those are going to be below the Concordia line. It can be above, that's less common. But the reason why those are off the line for the Concordia is because that you've had lead loss from metamorphism. So if you have several ages in there and you're able to create some sort of a line, this is called a discordia, and those will connect those discordant points, and the intersection will give you the time of the original crystallization. So it's pretty neat, really, really handy stuff if you have these elements available in your rock. Having multiple dates will kind of underscore the very, very complex history that goes on for some of these very old rocks. So let's look at some actual data. This is a lot, but hopefully after I explained that, we'll be able to just take the takeaways from it. So these are the rocks from Wyoming. The oldest rock they found there was about 3.5 gigaannum, so billion years old, plus or minus 3 million years. So it's actually pretty concise for this sample. And so there was also an age that was measured on here that you see this as separately labeled point. And what they determined is that because these crystals were off the track for the bulk of the rock, they interpreted these as being xenocrysts. So xeno meaning alien, they're not from outer space, they're just from a different rock unit. So they interpret those as being from older crust that eroded, and then those detrital zircons were entrained within this other rock. So if we're moving to Minnesota, what we see here is that the oldest rock here was about 3.5 gigaannums, and then there was also another unit that was about 3.36 billion years old, which doesn't sound like a lot unless you realize that a billion is pretty big. So what they interpret here is not that, oh, these are the same. They actually interpret that these two ages represent different things. And there's a third date at 2.6 gigaannum where these two different rock units were actually combined. So that's why there's multiple dates that seem correct here. And lastly, this is the unit from Michigan. And this is kind of similar to the last one. There were age groups at the 2.4 gigaannum and 3.6 gigaannum. And what they interpret is that those older ones are xenocrysts, again, from an older crust. So out of all of these, if they're trying to determine what is the oldest one in the United States, it seems like the clear winner is going to be the Waters Meet Gneiss. So that's the one that's the oldest intact rock. So the whole thing has the oldest age. But there are those xenocrysts that show that there was older crust here at some point in time. And they just kind of looking at the geography here, they determined that these rocks had similar histories, and therefore they were probably once from the same crustal block. And then this crystal block acted as a nucleus onto which the rest of the United States continent could be, or the rest of the North American continent could be formed. So it's a pretty neat study. And lastly, this is going to look familiar because this is Portland. We're going to talk about how volcanologists can improve urban climate resilience. So what this study was looking at is to see if there is a way that we can use some strategies that are used by volcanologists to kind of approach climate science issues, and looking at these specifically at the city level. The reason why they chose cities in the Pacific Northwest, so both Oregon and Washington and also British Columbia, is because in this area there's really robust environmental policy innovation, and there's also proximal tectonic hazards. So they kind of can look at the climate side and the tectonic emergency side at the same time. And what the study was talking about, or sorry, it wasn't a study, it's more of like an opinion piece. But what they were talking about is that even though the nature of climate disasters and volcanological disasters are different, these sort of challenges that a rescue operation would take are going to be pretty similar. So one of the things they highlighted is that volcanologists have this like built-in understanding, that you acquire about how to communicate geographic risks to people. And so this is one of many hazardous maps for the Cascades. This one's from Mount St. Helens. And another thing that volcanologists do really well is communicating hazard information to the public and to local communities. So this picture on the bottom is part of a picture from the local news in Ording, where they have a lahar drill yearly, I believe it's yearly, and the whole community takes part in it. So essentially with volcanology, volcanologists must use like innovative approaches in order to communicate these public events to people, especially ones that are outside of people's lived experience. So what that means is like most people have not experienced a volcanic eruption firsthand, but you have to be able to communicate those issues to people and make them care and understand. So some of the things that they highlighted that volcanology does really well are things like the localized risk mapping. So this one's similar to the one I showed before. This one is for Mount Baker, but essentially they have areas that are delineated for risk of different hazards, and that's something that really needs to be done for climate effects as well. There's also what they called, I really liked this wording, a border agnostic approach. So the idea is that Mother Nature doesn't care where we draw our political boundaries, so we need to kind of understand that and act accordingly. Also, they highlighted the importance of collaboration over colonialism. So what they mean with that is that not just ignoring the local perspectives, people who have either currently live here or whose ancestors have lived here for a long time, working with those people and not just speaking over them because, we're scientists and we're always right. No, you need to use the local knowledge. And that's how you're going to be able to communicate with people effectively. So this is an event that took place between the USGS and some local groups in Indonesia. And then also, the rapid response and capacity building that happens with volcanology. So in times of crisis, people mobilize very quickly. And so that's something that they want to be able to take and repeat and kind of plan for climate disasters. So specifically with climate things, it's going to be focusing on long-term resources and having just plans in place. So essentially, to wrap it up, what the article calls for is just this need, this need for collaboration between volcanologists and city resilience officers, which I didn't know that was a thing until I read this article. And yes, we have those in Portland, and they meet regularly. So at least once or twice a month from what I could tell. And yeah, volcanologists are going to be people who can provide valuable insights to help people prepare for climate crises and kind of the increasing dangers that come along with climate change. So that's going to wrap it up. And so I put this picture of the Josephine Ophiolite in here just to kind of wrap it up. That's a place I really keep meaning to go every time I drive between California and Oregon. But yeah, check in next month and we'll be doing kind of the same thing.
All right, thank you, Alyssa.
Mhm.
And Lori wanted to know, stromatolites are estimated around 3.5 billion years in age. They're on sedimentary rocks, but wouldn't these be considered older? And Frank responded that the actual oldest stromatolites are found in Australia.
I'm a little disappointed that the Mortonites didn't come in first or last or oldest. It's one of our downtown geology rocks or downtown building stone rocks. And so it's the oldest rock available in Portland that we know of because
There
it's
you
on the
go.
buildings downtown.
So I've actually got a couple comments on the first part of it with the leaking rivers. That's something that our Oregon coast with our dune sheets, we do experience influx of salt water into our coastal cities and into their water sources. So this isn't just a Brazil issue. This
Yeah.
happens right here in Oregon. I don't know quite what's going on down at Florence, but I know that was a bit of an issue. Uh, Reedsport, Florence neighborhood for a while because of our dune sheets with all of our sand, another geologic feature. Asher has got a question. What's your thoughts on the fundamental difference between volcanoes in the Pacific Northwest and Southeast Asia? Also, there is a lot of earthquakes in Alaska and the Ring of Fire. However, it seems to be disconnected to the Pacific Northwest, like the gap between Alaska and Washington. So what causes the large gaps between the volcanoes?
I can speak a little bit on that. Yeah, so some of the differences for volcanoes around the Pacific Ring of Fire are going to be caused by differences in how plates are subducting. So that's one thing. If your plate is subducting shallowly, that will cause volcanism in one area. And if it's subducting kind of less steeply, then it can either cause volcanism in another area or it can sometimes shut off volcanism altogether if you've got something like a flat slab subduction situation there. And so kind of the differences in volcanoes and where they occur around the Pacific Ring of Fire is going to be dictated by that. And also because not every area along the plates, like the Pacific Plate, not every single area is like subducting. There are some other areas where you've got more like side to side motion. So it's just kind of a complexity of like subduction geometry is one of the biggest ones.
Lori had a comment that she saw lots of stromatolites in Glacier National Park. So that's actually a lot closer to us here in the Pacific Northwest, up there in Montana. And Lori Green, thank you for speaking up on that. So some wells south of Florence are seeing saltwater incursion. The city's wells are fine. Because I remember this was dealing with the Oregon Dunes National Recreation Area, and the water wells there were having some issues. So that would fit in with being a little south of Florence with some water quality issues.
Yeah. Well, and this kind of highlights why it's so important to read about things that are done in other areas is that most likely that is not the only area on the entire planet that is experiencing that kind of a thing. So seeing what kind of work people are doing in other places can really help us to not have to do the entire thing all over again if we end up coming into the same problem somewhere else.
Well, those were three fun topics, Alyssa. Thank you.
Thank you.
Well, it is my pleasure to introduce Dr. Emily Cahoon, and I, for one, am really looking forward to learning about our lithium mines here in the Pacific Northwest. So, Emily, it's all yours.
Thank you so much, Carrie. And Alyssa, thank you so much for, I think this was the first like proper geology in a nutshell that I attended, and I learned so much. So thank you. That was awesome. But yes, thank you so much for the invite. And so I am going to talk to you for the next 25 minutes about lithium mining in Oregon. And Paul and I talked a bit about workshopping this title and different variations of it. We thought about calling it like the future of lithium mining in Oregon, but I was a bit hesitant on that because I don't want to pretend that I necessarily know what's going to happen. And so I sort of, right, this is the title, but I sort of morphed it in really what I'm going to talk about for the next 25 minutes is sort of lithium and its function and significance as an element in economic geology, why we care about it, mining activities, and sort of how those change as a result of like how lithium is in different rocks, and specifically in Oregon, the deposits we have and why we have them. This picture was one I took actually not even a year ago when I was out in McDermott. So that will be the place I'll be talking about. And don't worry, I'll show you where it is on a map. And it's a really interesting sort of geological landscape. I feel like I consider myself someone who is pretty familiar with different parts of the state and general geology. And the geology at McDermott Caldera is just unlike really any other place I've seen in Oregon. So far, some of the work that I've done there has been a very collaborative project with a variety of different entities. And although I'm not speaking on behalf of that group, I would just like to acknowledge that anything I'm going to talk about and the knowledge that I have is not just from me, it's definitely sort of a collaboration. So when we talk about lithium, right, this is an element, and sometimes you may hear certain elements referred to as critical minerals. So this is our fun periodic table. Anything here in black and green is sort of highlighted as a critical mineral. I personally don't love the name critical mineral because in fact, a lot of critical minerals are actually just elements. So I feel like when we're thinking about science communication, when we call them critical minerals, we're almost already starting at a deficit. But lithium is Li, it's up in the upper left-hand corner here. And actually it being really light on the periodic table already introduces some complications that make it just sort of hard to measure. So I feel like because we're talking about, because this is in the context of critical minerals and elements, I wanted to make sure that I was at least highlighting kind of where lithium sits on the periodic table. And I should say that everything listed here that is highlighted as a critical mineral, again, most of the time just elements. This is from 2022. And part of the reason I'm showing you something that's a little bit outdated is that with a number of, we'll say recent economic changes, these things what is listed and what is considered critical can change actually pretty rapidly. So specifically in batteries, so electric batteries, there's a lot going on here, but this is sort of just a infographic that came out a couple years ago, and it was really focused on electric vehicles in particular, but specifically batteries, and what proportion of them are different elements or minerals. And basically, lithium becomes a really important part of a variety of different types of batteries that you find in electric vehicles. And I should note that while this is a picture, an infographic of an electric car, of an electric vehicle, these critical minerals are also incredibly important in solar panels, just general energy storage. So things like lithium, cobalt, nickel, manganese, and you can see in this case, right, graphite, right, that is a mineral. So these are all different critical minerals, but lithium is actually the most important, or you could say ranks the highest in criticality. So I want you to look at this kind of green, yellow, and red graphic on the left, and effectively along this x-axis here is supply risk. So that means, right, how kind of available are these different critical minerals, or again, elements? And then on the Y, that particular critical mineral's importance to energy. So when we look at those two things, lithium is basically ranking right up there really high. Nickel is also up there. And I should say this particular matrix came out of the Department of Energy in 2023. So again, right, this is not today, but I do want to mention that lithium is, even though prices of lithium have shifted, and we'll talk about that, on the right, so about 3 hours ago, I went into Google and I basically searched, I think I searched lithium mining or lithium mines and just went to the news tab in Google. Keep in mind that I am in Charlotte, right? So my searches are going to be a little bit different just based on my geographic location. But what I want to highlight is basically all of these are links to different news articles. And I want to highlight that in each case, it's talking about a lithium mine. So this first one is about a lithium mine in Arkansas. The second one is a lithium play, we'll call it, in Nevada. One on tech and lithium sulfur batteries. Right, this fourth one down is in West Arkansas, and then the one at the bottom is Ontario. And these are all, if you look at how long ago they were, I mean, we're talking right within the last 48 hours. So I know that's kind of like a busy figure on the right, but what I just wanted to do is I literally just put that into Google on the news tab, and these are the things that are coming up. So, you know, when it comes to critical minerals, it's not something kind of happening in the background. Like, this is very active. It's, you know, happening every day. And really, a lot of these critical minerals are important, you know, for batteries, but also to fuel the clean energy transition. And a lot of the technology we hear about every day, these critical minerals are very important in fueling that. But I really want to highlight here that lithium sort of basically ranks the highest in criticality. And again, this was as of 2023, right? Because the economy is always changing. And so, right, who cares about lithium? So I was saying that it was going up, right? And if we look along the x-axis, right, so this is through time, 2010 is all the way on the left, and you'll see 2022 is all the way on the right, okay? So still, you know, a little bit dated, a couple years old, right? And it seems to just be going whoop, right up. Prices going up, and this was probably around the time that I think, if anyone is paying attention to like funding calls, there was a lot in various entities about, you know, funding for lithium research. Well, interestingly, and it's hard, right? It's hard to find sort of an infographic that looks the same that you can just sort of add on to. So if you look more recently, if you Google the prices of lithium, they have come very far down. It is for a variety of reasons. I don't think you could say it's just one, but I want to highlight here that while lithium did rank the highest in criticality, you know, a year and a half ago, a lot has changed. That doesn't mean that it's still not going to be important, but the economy, right, is driven by humans, and so it's changing every single day. And I think it's really important to highlight here too, because when it comes to lithium mining and how far those activities are progressing in Oregon, it is going to be a function of the price of that commodity. So thinking about lithium, right, as a commodity, the how fast and how kind of active those activities are at some point is going to be a function of the overall price. So that's kind of just right, basic of lithium, critical mineral. Prices have fluctuated. That's kind of the, I'll use Alyssa's terminology, it's sort of the nutshell of this first part. Okay, so where do we find lithium? And we will get to the fact that we do find it in Oregon. Lithium is found in 3 styles, and the colors here correspond to the map below. This came out of a study from Tom Benson et al. In 2023. Tom is now I think he's the global chief of research for Lithium Americas, and he had a paper that just kind of highlighted a number of different global sources of lithium. And so 3 major types. So the first type is what you'll sometimes hear called pegmatites. Lithium is concentrated in spodumene, which is a lithium-bearing pyroxene mineral. But this is hard rock. This stuff is really hard to mine. You have to drill. The grades of lithium ore, meaning for every amount of rock you have, the amount of lithium that's in it, are typically higher, which is great, but it's going to cost a bit more to get out because this is hard, dense rock. The second type is the brine, sometimes called evaporite. Sometimes you hear them called salars. They're often found on the western coast of South America. frequently in the Atacama Desert. And I believe the picture that was on the little sort of poster for this talk, right? It said lithium mining in Oregon, was actually a picture of some of these brines where you get these sort of like impoundments. So if you've ever seen a lithium mine that has kind of impoundments of water, it's typically these brines. Again, most of them are along the west coast of South America, frequently in the Atacama Desert. Now, so these red types, these hard rock in spodumene, and these blue types here, these evaporites, these two, up until, I don't know, maybe let's say 5 years ago, were the most commonly mined type of lithium deposit. And it's only been very recently, right? Because you don't look for what you don't necessarily expect to be there. We've discovered that there's actually sort of a third type. And these are called a whole bunch of different things in the literature. Sometimes you'll hear them called volcanosedimentary, which is how I list them here in green. Sometimes volcanic clays, sometimes volcanic mudstones. But effectively, lithium is bound in these clays that are derived after a volcanic event, so after an eruption. Lots of discussion about exactly how the lithium is getting in those mudstones or those clay stones, but it's a very sort of, and I say newly discovered, again, last, we'll say 10 years. That's not to say that someone didn't notice something, decades ago. It's just sort of really hit the literature and hit, I think, the scientific community as, hey, this isn't a one-off. This is actually a new style of deposit. So because of this, we have a ton to learn, and none of these are actively being commercially mined, right? And when I say that, I mean the stage of mining where there's a processing plant, the rocks are being taken out of the ground, we know how to get lithium out of the rocks. It's not in that sort of like active commercial production phase of mining. That doesn't mean that there's not still exploration phases. So when I say none of these are currently commercially mined, what I should have really said is none of these are currently commercially like producing lithium. They're very much in the exploration phase. And like any mine, as arguably it should be, right? If you're going to really disturb the land, there is also a huge series of permitting. So this third type, this volcanosedimentary, is particularly the style that we're going to focus on in Oregon. And it is, again, sort of worth mentioning, a little bit of a caveat here, that whether or not something is economically viable changes effectively every day to some degree. I know we kind of already said that, but I think it's worth mentioning again because, as something is actively being mined, mining activities could kind of stop. Exploration could stop for a year, 2 years, 10 years, sometimes 20 years, sometimes I think even longer, when then we can come back with, maybe the price of the commodity is different. Maybe we have the technology that can get it out of the ground for less money, or maybe, there's been advances in technology to actually process the material, meaning maybe you can get the rock, but how do you get the commodity that you want out of that rock? So yeah, even though right there was a period where these volcanosedimentary deposits were very much on the exploration side, and activities are still going on, because of the prices right now, we're in a little bit of a lull. Okay, so these three colors, again, kind of getting an idea of where we're looking. And I do want you to notice, I'll go back one slide, that there's not a lot of green, right? So this new kind of style, that doesn't mean they don't exist. It just means we haven't maybe found them yet, right? You don't necessarily go looking for what you don't expect to be there. So same color scheme, right? I want to just give you an idea of what these things look like, either in hand sample or kind of on a larger field scale. So thinking about this hard rock, this pegmatite, spodumene. So spodumene is particularly the mineral we care about that hosts the lithium found in pegmatites. So those two pictures on the left, and there's like a little call out for spodumene in particular. Again, it's a pyroxene. These are hard rocks. These are, right, you got to drill down. That's not to say some couldn't be found at the surface, but any active spodumene, right, lithium mine, they need to have heavy equipment to actually drill down. And it's interesting actually being in North Carolina because there are active spodumene mines in the state, which is just actually just kind of interesting that they're here. And I actually even have a friend from grad school that works at one of those companies. So I guess small world, right? Brine, so the blue one here, and this is probably kind of like the picture that was on the poster for this talk, because these deposits are more common. Yeah, I think I would say they're more common in terms of new mines that may become active, and part of that is because it's right at the surface. They don't have to drill down very far. Now, the downside of this is that, and when I say the downside, I'm not talking yet about any of the environmental impacts, but that the grades are lower. So per rock, per some volume of rock, there is less lithium typically in the brines than in those spodumines, but you don't really have to drill down. So, right, pros and cons. With the volcano sedimentary, so these green ones, both of these pictures, if I remember correctly, I took both of these in the last summer and then the summer before, so 2023 and 2024. And I don't know about y'all, but these are some not so pretty looking rocks, right? You might see this in the field and be like, nah, I'm good, right? It just kind of looks like, I mean, it looks sedimentary. You could even maybe say it kind of looks like a carbonate. It's super friable. But in here, right, it's not the entire thing, but in here you get these intercalated kind of, it's really interesting. They're almost like sticky clays. And again, if you saw this in the field, probably, at least I know the last thing on my mind would be like, I wonder if I should take a chunk of that. Like it doesn't even really look that cool until you get an analysis back. And the lithium is in, the parts per million is in like the thousands. And sometimes, like 10,000. So it's there, but the rocks themselves don't look that great. But kind of showing you a very much a variety of lithium doesn't seem to be very particular, right, in the kind of type of, well, I mean, it is particular in the type of rock, but this is definitely a pretty diverse array of rocks and sort of geologic environments that can contain them. Okay, so we're thinking about lithium as a critical mineral. We know that the prices have fluctuated a lot, and we know that there are three main styles of mineralization. You could call these deposit types too. Okay, well, what is happening in Oregon? Because if I'll keep going and I'll show you that this is a map that hopefully we've all seen in some capacity over the last, I don't know, couple years. So this is the Pacific Northwest. We have Washington, Oregon, Montana, and this beautiful gray polygon is the extent of the Columbia River basalt. So very large outpouring of basaltic lava that covered a large part of the Pacific Northwest between approximately 17 and 15 and a half million years ago. And if you notice, there are these wonderful, well, one is green here, and it's green for a reason, but wonderful little circles, and these are all calderas that go up to present-day Yellowstone National Park. Effectively, underneath this is where the magma body that fueled the Columbia River basalt eruptions is sitting today. So if we look at the ages of all the calderas between present-day Yellowstone National Park and the Columbia River basalts, you'll see this beautiful sort of like temporal linear kind of chain where you have, right, Yellowstone today. You have the High C at about 6 to 5, the Peekaboo at 10 to 7, Twin Falls, Bruno Jarbidge, Owyhee Humboldt, right? And these are just getting older and older and older. And McDermott effectively is the oldest caldera forming eruption associated with the Columbia River basalt province. Now, if somewhere you're thinking, well, I know of other places where there's calderas of that age around, you're absolutely right. But in this really nice chain along the Snake River Plain, the McDermott caldera is the oldest caldera forming eruption that happened along that chain. And I have it highlighted green here because it is McDermott where effectively the largest domestic source of lithium is located. A couple things geologically I want to take away from this, right? Earliest caldera forming eruption associated with Yellowstone. Spatially, if you look at this fun little green polygon, you'll notice it straddles state lines. That actually becomes significant from a mining standpoint. And the caldera itself formed over about 1 million years, and there's been a variety of different eruptive products, tuffs, ignimbrites, that have come out as a result of that eruption. And lithium, particularly at this caldera, is concentrated in, right, I said it was volcano-sedimentary. The lithium is actually bound in these like I was saying, kind of ugly volcanic clays that are inside the extent of the caldera margin. So if you're inside the caldera and you're inside a clay, that is where the lithium is contained. Now, it doesn't expose itself everywhere. At some point, it sort of dips down. But this is where we're finding the lithium. And I have a little sort of info, I guess, a little cartoon here, schematic showing to give you an idea of, right, as a plate moves and you have a hot spot, that you get this age progressive trend. So yeah, couple things to take away, both geologically and spatially. And we're gonna kind of zoom in on this kind of area a little bit more, because right, I said that it was right straddling, you can see it kind of straddles this state boundary. And again, earliest forming eruption of the Yellowstone plume. Okay, so same thing. I should have changed this to green, not blue. That was my fault. What we're focusing on is trying to characterize the timing and the processes, so like volcanically, magmatically responsible for getting lithium in these mudstones. So this is a picture just right off Google Maps. And if you look at the town of McDermott, which you can kind of see is, do I have, oh, lovely, I can annotate here. And I'll make this green. So if you can see, we have the town of McDermott right here. If anyone feels so, like they want to go on Google Maps and check it out, you can see so beautifully the extent of this caldera. It almost looks like a keyhole that's kind of right on the state line. And I'm mentioning the state line for a very specific reason, because when it comes to mining activities, there's a few things that this state line happens to be, well, can sort of dictate. And one of them, I'm going to start from the bottom here, is actually the mining regulations. So the difference between Oregon's mining regulations and Nevada's mining regulations, and just when I say mining regulations, I'm just kind of speaking more broadly, right? They're different, and that actually, I'm going to go kind of up this list. That actually dictates which mining company is operating. Because if you're a mining company and you want to, you're interested in this new style of deposit, you probably don't want to navigate, right? Because again, prices of lithium changing all the time. You probably don't want to navigate multiple sort of like bureaucratic processes. And right, these processes are in place for a reason. But effectively, what has happened is there's one major mining company operating in Nevada, so on the south side, and there are a few, but one major company operating on the north side in Oregon. It gets also a little confusing because the company operating on the south side, which is Lithium Americas, it's still at McDermott Caldera, but they specifically call their deposit Thacker Pass. So if you've listened to NPR or you've heard anything about Thacker Pass, it is effectively you can kind of think about it as just this, not the entire south side, but basically lithium mining activities that are going on in Nevada at McDermott. What makes it a little also confusing is that the company that's operating in Oregon, and they are at different stages than Lithium Americas, right? Because those mining laws are different, is a company called Jindalee. Now, Jindalee also operating at McDermott, right? They're operating at the north side, but they call their deposit McDermott, right? So two companies, the company in Oregon calls it McDermott, but the company that's operating in Nevada calls it Thacker Pass. Right? So it just, if you hear these names, it can just get confusing. What is actually kind of interesting from a deposit, right? So they're both the same kind of deposit, but when it comes to the specific mineral, obviously when McDermott erupted, it did not care about state lines. State lines did not exist, right? We just made those up, right? And Alyssa made a point about this, right? Earth doesn't care about where we're putting our geographic boundaries or whatever. But what's interesting is the specific mineral that contains lithium that Lithium Americas is extracting in Nevada is actually slightly different than the lithium containing clay mineral that's in Oregon. Now, it's obviously not perfectly by state lines, but it happens to just kind of be that one clay is, and we're talking about clay mineralogy. So these changes are to even myself, who I would self-identify as a mineralogist, I would not be able to tell the differences between these clay minerals. They're very, very subtle. But it's interesting because how that lithium is bound in that clay mineral actually influences the extraction processes and how we get lithium out of it. So how Lithium Americas is going to get lithium out of illite down in Nevada is going to be different than how Jindalee or another company is getting lithium out of the clay minerals it has, which could be smectite or it could be hectorite. These are all clay minerals, minor differences to, I think, an average geologist, but actually has some pretty, I would say, legitimate implications when it comes to the processing side and how much money and how much water it's going to take to get the lithium out. So it's just kind of, I mean, I'm sure there's other cases of things like that, but it's just kind of interesting that here's a place where a deposit straddles sort of right, again, a random boundary we have created, and actually, you could argue maybe makes some, kind of breaks the project up and breaks the science up into different ways. Okay, and the last thing I just wanted to highlight here is this is a map, a geologic map that was done. I don't expect anyone to read it. I just kind of wanted to highlight the different colors to give you an idea of the kind of degree at which it's been mapped. And funny enough, a friend I went to grad school with actually was mapping this as part of his dissertation now maybe 12, 15 years ago. But it's kind of these orange colors that in Oregon that we're the most interested in. So that's where these clays are located. Down in the south, I believe it's some of this like lighter shade of yellow, but I shouldn't speak to that because I'm much more familiar with the Oregon side. So it's these orange, and again, it's these clays. And the picture I showed you earlier, you would walk up to this outcrop and be like, I definitely see some stratification. But just to highlight, they're not, exposed everywhere. And that's not to say that they're not at some depth. These clays are forming from a lake that basically existed within the caldera, and also creates a lot of questions of like, are there other calderas that are like this? Now, I'm not saying we should go looking for lithium everywhere, but you start to think about sort of the geologic recipe needed to create a situation like this. And it has to do with magma composition. It has to do with proximity to cratonic crust, the dimensions of that caldera, how sort of restricted from groundwater influx, maybe rain, is it to actually create that lake? And so there's sort of two hypotheses how lithium is getting into these clays at McDermott Caldera in Oregon. And one of them is basically whether or it has to do with whether or not the lithium was moved around a lot post eruption. So did it happen immediately after eruption and sort of was just concentrated in those lake sediments? Or did it take some time and the lithium actually sort of like percolated out of the lake into the sediments as it was forming. In either case, the kind of understanding is the lithium is coming from the magma originally. It's just a function of what is the process and what is like the perfect Goldilocks set of conditions to get it in there. So the kind of take home points and what could be happening in Oregon's future, I think it's that lithium demand, even though the prices are down right now, it's expected to increase pretty significantly over the next decade. We do have the largest known lithium deposit, and it's in Oregon, and again in these volcanic mudstones or claystones, volcano sedimentary deposits. It's a new style of resource, so I think in terms of the future of lithium mining and what's going to happen, there's a lot to figure out to get us to a place where we know, sort of also like the most socially responsible way to extract this. And that I didn't at all touch on the people who would be affected by that, right? Because there are people that live in this area, and lithium mining does have it's not like any type of mining. It is not sustainable, right? No mining by definition is sustainable, and there are environmental impacts, there are impacts to people, and so there's a lot that I think needs to be learned, right, and it's going to take time because knowledge of these deposits and the technology to extract this lithium, like many mining practices, has not actually advanced in quite some time. So I think I'm almost perfectly at time, and I will end with that.
Emily, that was absolutely delightful. A great explanation of lithium, and coming from a mining background, I think a lot of people don't realize just what that whole process is, that you don't just jump into production. You have to start from the exploration phase. And good point on, we don't know how we're going to extract that mineral. You ended up with some good questions. Just a minute, let me
Oh, I
roll
didn't even see the
back.
chat.
So right off the bat, Asher was curious. He noted that the USGS list for lithium doesn't actually list lithium on deposit. It's on their map for USGS.
I don't know. That is an excellent question. I will say I know that this database is in the process of being updated. I mean, I guess you could argue like all databases. I don't know. That's an excellent question.
Good
I
question.
don't know why they wouldn't list it unless they're listing it. I have to play around on the map, but unless they're listing it as something else, if they're listing it as like spodumene, not lithium.
Mhm.
But I
Or
would
a
have to
special
look into
critical
that.
mineral corner somewhere.
Yeah, I don't know.
Yeah. So, John, you asked, is there an explanation for lithium enrichment in the volcanic soils? I think Emily touched on that, but did you?
So yeah, I barely got to it at the end. This is still very much the focus of the work is right? So what is that geologic recipe required to get the lithium into these mudstones? Effective, and you said what chemical, so these clays, sometimes it's easy to think of clay as because it is a size, right? Clay is a size of something, but there are also a ton of clay minerals. I will give a shout out to our new state geologist, Dr. Rory Destorat. He is a clay mineralogist by training, and knows the differences between a number of clay minerals. So depending on which part of the caldera you're in, there's hectorite, illite, and smectite, and those are kind of the three main clay minerals that lithium is bound in. There are some other odd ones, but effectively it has to do just almost sometimes like what layer the lithium ion actually sits in. And so in terms of an explanation, there's sort of two ideas. In both cases, the lithium is coming from the magma originally. So that is part of the reason why we think the composition of the magma is relatively important. But being in these clays, so the idea is that right, so it erupts, it forms a depression, it starts collecting water. Now you do have to have a certain set of conditions, could say sort of like spatially, to kind of create a situation where you are um, sort of forming a clay. To get these particular minerals, the idea is that you don't have a lot of outlets. So there's not like a lot of way for kind of water to leave. And actually, I think I may even have a slide about this. But yeah, you don't have a lot of ways for water to leave. It needs to be relatively alkaline, the water itself. And so it's whether or not the lithium is getting sort of like, as that clay is forming, the lithium is kind of coming out from, we'll just say like below. You can kind of think of this as like a more short term or short time scale. And then in the other situation, the lithium is actually, you could think of it almost like it's in the ash, and then that is, I mean, I'll say the ash, but sort of in some products, that gets put into the water, and then over time, that lithium kind of gets put into the clays, and that is more of the longer time scale. Those are the two ideas, and I would say there are bits of observations that are kind of at odds with one another. Now, some of the work we've been doing on dating, trying to figure out, because there's an ash unit like above and below where this clay is, so we've been trying to figure out like what time did this clay actually precipitate? And it gets a little weird because a lot of the ashes that are there they're getting minerals from elsewhere, from other eruptions. So you could date something, and actually to Alyssa's point of like, right, you can date a zircon, for example, but this eruption didn't produce zircons. So cool, you can date a zircon, but you're dating a zircon that came from, over there. So you have to be kind of smart about when you're looking at, we did different types of single crystal work where we basically dated a ton of different sanidines. So effectively a type of feldspar in one of the clays to try to constrain when this clay formed. That doesn't answer the hypothesis, or it doesn't answer the question of like, was it this long-term or more short-term? But it does enable us to constrain at least when it formed. And so far we can tell based on some of the drill cores that we have or had access to from one of the mining companies, that it falls within stratigraphy. But again, you almost like you're trying to create a framework or a conceptual model of like a timeline, and then trying to almost like prove your hypothesis wrong to figure out what is more likely. That was sort of long-winded. Sorry.
Well, actually, when you read Asher's next response to that, you basically covered and picked up Asher's questions about the volcanic ash. So, Wes, I presume that other calderas on the hotspot track have been investigated for the presence of lithium. Is the age of the caldera, oldest being McDermott, a factor in this? And that was one of the questions I wrote down for myself as well. So do you think you're constrained to the 16 million, or, we got this 29 and a half puppy that's sitting right here in Central Oregon. So is there...
So Carrie, I actually submitted an NSF proposal to look at those calderas back in 2023, and it got really close, but it wasn't funded. That was, I don't know if I should have shared that, but so I have a failed NSF proposal basically proposing exactly that. So, on the Crooked River. So yes, 100%, I think those are of interest. There's some calderas further north in like the Three Fingers area. Those, and depending on which paper you read, is how they're slicing and dicing caldera names. I think those are of interest. But to the question of the age, I don't necessarily think, well, I don't know, to be honest, whether or not it's a factor. But if you think of like the Goldilocks situation, again, being like the geometry of the caldera, its age, its composition, its proximity to cratonic material, right, its source, all of these things, it's I think if you were to look at another caldera that was potentially prospective, I would want to just only change a couple variables. So I'd want to keep the age roughly the same, the proximity to cratonic material roughly the same, the geometry roughly the same, but like, and maybe the composition, and let's see how, does it change? Is it not there? And I think to some degree that can start to give you an indication how much is reliant, like, or how maybe unique of a situation this is, or of the variables, which of those variables are the most important. I don't
Exactly.
think age is a super factor,
But
maybe
it's the
other
other
than like
criteria.
preservation potential, but I I know people have talked about investigating other calderas for it, but I don't. I could be wrong. I don't think anything's been done. Part of it like breaks my heart too, though, because you think about like the Snake River Plain and everyone just going out looking for. I don't know. So
But and we've got some really cool deposits up in the Vantage area up in central Washington that it's like, whoa, what have we got going on there? Could that be so?
yeah.
So, okay, moving on. And I think you did talk about this. Which of the three environments, hard rock, brine, volcanic, have the highest concentrations? Was it the hard
Typically hard
rock?
rock.
But that's
Typically.
the most difficult to extract given the cost.
Yes.
You pick that up right?
But yes, no, you nailed it. Nailed it. But the ore, you could say the ore grades have the highest concentrate. Like the grades are the highest. So they have the highest concentration of lithium. Um, but yeah, it's a little bit harder to get to. And I didn't really talk about processing at all, other than that it can get complicated. Often, especially particularly in Oregon, right? So you can imagine you're out in eastern or southeastern Oregon, right on the Nevada border. Um, a lot of these processing, they take a ton of water. Water is not necessarily abundant. Also, what water is there, you don't exactly want to destroy. And in some cases, there are processing or processes, I should say, that require various amounts of acid, like sulfuric acid, which is very expensive, or it can get to be very expensive to the point that maybe you can clean up your ore faster and separate lithium, but you just spent millions of dollars on sulfuric acid and like you're out of money. So
Yeah.
the
And
price of lithium goes down and you're in the tank.
actually, you just hit on Anna's comment about groundwater and how much you might need in order to be able to do the process. And Alyssa was going, "Yep, that's a definite possibility.
Huge.
Easy to forget those factors that go into processing." And there's some really nice kudos, Emily, for your presentation.
Made me
Okay.
want to be a clay mineralogist, Alyssa. That is impressive because I don't know that I could ever be a. It's so
Okay.
like,
Well, for a few minutes at least. I mean,
yeah.
I'm not
So,
giving
so
up
I
my rocks yet, but
so I think this last one is pretty interesting. Lynn, is how about the volcanic ashes that make up the John Day fossil beds as candidates for lithium deposition? I mean, they have moved to a new place, but they've also been soaked by a heck of a lot of groundwater over time with all of the debris flows and things.
They have. I I think they probably had or they could have had a lot of lithium in them, but I think to concentrate in one kind of to have your because you kind of like have your source, but like to have like almost the um what's the word I'm looking for? Like almost like a reservoir kind of for the lithium to
Base.
deposit. I think you do need some sort of confining unit that is, you know, not sort of just like laterally continuous, but actually bounded. And so I wouldn't be surprised, but I don't know. I would say it's a possibility.
So the take-home message from what you're saying is we're still learning.
We're still
This
very much
we're still learning. Oh,
figuring it out.
this has been absolutely delightful between Alyssa's topics and the lithium mining. Thank you so much, Emily, and thank you,
No,
Alyssa.
thank you.